Are you ready to dive into the intricate world of kernel programming? This video explores how to write programs at the kernel level, unlocking powerful capabilities within the operating system. Discover the tools and techniques essential for mastering kernel-level development. Kernel modules are pivotal in extending the functionality of the base kernel. They allow developers to add features to the operating system without altering or recompiling the entire kernel, promoting flexibility and modular design. They allow interaction with hardware like block and character devices, block devices like hard drives, and character devices like keyboards or serial ports rely on driver modules that handle communication between the hardware and the kernel, enabling proper data transfer and control. These modules can be loaded and unloaded without rebooting the system. This dynamic capability, using tools like nsmod, rmod, and modprobe, allows system administrators to update or test modules on the fly, improving uptime and maintainability. Writing kernel modules requires an understanding of the Linux kernel architecture. Developers must be familiar with kernel space versus user space, memory management, system calls, and driver interfaces to create safe and effective modules. Debugging is crucial to ensure stability and performance. Since bugs in kernel modules can crash the entire system, careful testing with tools like dmisk, printk, and kernel debuggers is essential for identifying issues and maintaining system integrity. System calls serve as a bridge between user-level applications and the kernel. They enable tasks such as file manipulation and process control. Writing system calls requires careful attention to security and stability. Developers must ensure that system calls are efficient and error-free. Testing is vital to verify their functionality and performance. Writing a kernel module involves creating, loading, and unloading processes. This includes writing the module source code, compiling it into a loadable kernel object (OTHM) file, and using tools like nsmod, rmod, and lsmod to manage it within the kernel at runtime. Device driver programming is a key aspect of interacting with hardware. Drivers serve as the interface between the kernel and hardware components, handling input-output operations, data buffering, and interrupt handling for devices like storage, network cards, and USB peripherals. A simple example includes a module that prints "Hello World." This introductory program demonstrates module initialization and cleanup routines using init_module and cleanup_module, WUSH, or modern equivalents like module_init and module_exit, plotlouise. Extended examples involve system calls and device drivers. More advanced modules may register character or block devices, implement custom system calls, or interact directly with hardware registers, requiring a deeper understanding of the kernel's internal APIs. Testing and debugging are essential for effective module development. Developers use tools like printk for logging, dmisk for message inspection, and kernel debuggers to trace faults, as kernel-level bugs can compromise the entire system. To write kernel-level programs, a Linux OS like Ubuntu is needed. Kernel headers and GCC are essential tools. A virtual machine provides a safe testing environment. The make utility helps in compiling modules. Proper setup ensures a smooth development process. Creating a simple kernel module involves writing a C program. This program logs messages when loaded and removed. The makefile is used to compile the module. After compilation, the module is inserted into the kernel. Checking system logs verifies its operation. Kernel modules can interface with hardware using specific APIs. These APIs are provided by the Linux kernel to enable safe and standardized communication between kernel modules and hardware components. Abstracting the low-level complexity. Writing drivers for USB devices or network cards is common. Such drivers allow the kernel to recognize, configure, and communicate with peripherals, enabling tasks like data transfer, connectivity, and peripheral control. Interacting involves reading and writing hardware registers. These registers control device behavior and status. Accessing them typically involves using functions like IOREAD** and IOWRITE** WUT. to safely perform input-output operations in kernel space. Handling interrupts requires careful coding. Interrupts signal the CPU when a hardware event occurs. Proper implementation using a request_IRQ and free_IRQ ensures timely response without race conditions or deadlocks. Preserving system stability. Memory management is crucial in hardware interactions. Allocating memory with functions like kmalloc EO and managing buffers between devices and kernel modules must be done carefully to avoid leaks. Corruption or security issues. Testing in a virtual machine prevents system crashes. Avoid accessing user space memory directly. Always clean up resources like memory and devices. Use GPL-compatible licenses when distributing code. Following best practices ensures safe and efficient development. A system call is an entry point into the kernel from user space. It allows applications to perform privileged operations. System calls are crucial for accessing hardware and managing processes. They form the interface between user applications and kernel operations. Efficient system calls enhance system performance. Implementing a system call involves editing the kernel source. The syscall table must be updated with a unique number. A header file declaration is necessary. Recompiling the kernel applies these changes. Testing from user space verifies the system call's functionality. Compiling a kernel module requires a makefile. The module is loaded into the kernel using commands. System logs are checked to ensure proper loading. Removing the module involves specific commands. Testing verifies that the module functions correctly. Kernel modules extend functionality by interacting with hardware. They can be used to write custom drivers. Reading and writing to hardware registers is common. Handling interrupts and memory management are key tasks. Modules must be carefully tested for stability. Debugging is critical due to the direct hardware interaction. Kernel debuggers like KGDB are used for source-level debugging. Printic logging helps trace execution flow. Crash dump analysis aids in identifying faults. Dynamic debugging tools enhance testing capabilities. Stress testing simulates heavy load conditions. Fault injection tests error handling capabilities. Memory leak checks ensure resources are freed. Performance testing measures I/O and CPU usage. Proper testing ensures reliable kernel module operation. Using virtual machines for testing is recommended. They provide a safe and isolated environment to experiment with kernel modules without risking the stability of the host system. Snapshots allow quick recovery from crashes or errors during development. Modularizing code allows dynamic loading. Splitting functionality into separate loadable modules enhances flexibility, maintainability, and reusability. It enables developers to update or debug parts of the system without recompiling the entire kernel. Logging discipline keeps the system responsive. Using print tag responsibly helps in debugging while avoiding excessive logging, which can degrade performance or flood system logs. Log levels should be used appropriately to control output verbosity. Documentation and version control track changes. Clear encode comments, README files, and structured changelogs improve collaboration and troubleshooting. Tools like Git help manage revisions, support teamwork, and prevent regressions. Following best practices leads to efficient kernel development. Emphasizing safety, modularity, testing, and clarity results in robust, maintainable, and high-performance kernel modules that integrate well within the system. Kernel-level programs operate within the kernel space. They interact directly with hardware and system resources. Linux kernel modules extend functionality without rebooting. Writing these programs requires knowledge of OS internals. Proper implementation ensures system stability. A Hello kernel module is a simple example. It logs a message when loaded and removed. The makefile compiles the module. System logs confirm its operation. This example demonstrates basic module functionality. A module can read and display the system time. This involves interacting with system resources. The module logs the current time when loaded. This example highlights interaction with system resources. Kernel programming poses risks like system crashes. Testing in a controlled environment is crucial. Avoid infinite loops and invalid memory access. Proper cleanup prevents resource leaks. Safety measures ensure stable kernel development. Kernel programs can control devices like USBs. They enable custom system logging. Hardware interaction includes reading sensors and controlling motors. System monitoring tools report memory and CPU usage. User space interfacing uses ProCFs for communication. In conclusion, by mastering kernel programming, you can extend operating system capabilities and contribute directly to its functionality and performance. This includes writing loadable modules, implementing custom system calls, and debugging critical low-level operations. A strong grasp of OS internals such as memory management, process scheduling, and I/O handling is essential for effective development. These skills enable precise and efficient interaction with hardware and system resources. Kernel programming is a powerful tool for system-level development, empowering you to build high-performance, secure, and customized computing environments. Thank you for watching.